Good morning. Today let us discuss about an electronic design automation or EDA tool called KiCad. KiCad is an open source and a free to use EDA tool. Okay, so an EDA tool is used extensively. EDA tools are used extensively in the industry to draw these electronic circuits and to simulate those electronic circuits and to create the PCB layout, etc. out of those schematics. Okay, so you might be familiar with the breadboard flow. That is, you first draw the circuit on paper, and then you buy all these components that are required and a breadboard, and then you wire all those in your breadboard. Okay, but this is a little bit expensive and a cumbersome process, because sometimes what happens is that some of the components are not available. Okay, and you need to bulk order those things. It will not be available in one unit or two unit, and you will need to order a whole reel or a whole box of components which will have thousands of parts. And also breadboarding is limited to only through-hole components. And nowadays most of the circuits are fabricated with the help of surface mount devices, which are much smaller and which doesn't have these long leads. Okay, so breadboard flow has its limitation in terms of practical usage. Okay, so you need to find the component, and the component needs to be through hole in order to do a breadboarding. And increasingly more and more of today's components are becoming surface mount devices. And then this is one of the limitations of breadboarding flow. Okay, the other limitation is that at higher frequencies, the breadboard itself will have its own different behavior, which is completely different from the PCB behavior. Because these in breadboards you have adjacent metallic tracks which are like within 1 millimeter or 2 millimeters from each other. The distance between the two tracks within the breadboard is like 1 or 2 millimeters, and that will introduce capacitances between different signal lines which are not present, which may not be present in a PCB track. So the behavior, the high frequency behavior on a breadboard or of a breadboarded circuit can be completely different from that of a final PCB fabricated device or a fabricated circuit. And also it can show behaviors that can be completely different from that of your designed circuit, completely outside of what you are expecting. So because of these two limitations, in industry the use of EDA tool is for all these development purpose is much more widespread. And after going to industry, you will rarely see somebody actually breadboarding a circuit. Okay, so at these higher frequencies, so this is where actually newer circuits are built. Or for all the low frequencies, some standard circuit will be there, and you just need to copy it. Okay, for the high frequency, you need to build newer circuits, etc. And this is where the breadboard behavior is going to be completely different from the actual hardware behavior. Okay, so but this simulating these circuits in the EDA tool will provide a result that is much closer to the actual hardware. So by properly parameterizing the various components and etc., you can get a behavior that is much better than the breadboard behavior and much closer towards the real circuit. So because of these advantages, electronic design tools are the way in which circuits are designed and built in the industry. So let us try to understand what the features are and how to use a electronic design automation tool. Okay, so this is the KiCad window. What you are seeing on my on the screen is a KiCad project explorer window. Okay, so KiCad is basically a collection of multiple tools which are integrated together, so that so it will contain a schematic entry tool, it contains a PCB layout editor, and it contains a project navigator, and it contains a simulator. So all these are independent components, all of these integrated together and called as KiCad. Okay, so in here the workflow is like, the workflow under KiCad is like, first you will have to create a project file. So everything happens within a project file. Okay, so in order to create a project, you need to do a new project, and then you have to indicate a location where you want to save that project. So that will be a folder, and within that folder it will create a schematic file, and then a PCB file, and any simulation related files. All the files related to that project will be kept within that directory. So here I have already created a project, and this is the project file, and this is the project directory. Okay, so all the files related to this project, like the project file, the schematic file, the PCB file, and any simulation related files, all of those will be stored within this directory. So when you give a name, so while creating this new project, it will ask you for a location where you need to store the project. So I have given the location as this much, and then I have given the project name as RC integrator. Okay, so hence this particular directory was created, and this file also was created. Okay, so after the project is created, in majority of the cases you want to start from a schematic. Okay, and then you need to either simulate it, or you want to directly, without simulating it, you want to move into the PCB layout. Okay, so first thing in all the workflow is going to be a schematic editor. Okay, so let us familiarize with what all tools we have here and which one are the more important ones. So first one is the schematic layout editor, or the schematic editor. It is the most widely used tool in the KiCad toolkit. The second one is a symbol editor. This is if you need a new symbol, like an IC that is not modeled under or not already available within the KiCad. If you want to use that, it is from a small supplier who has not made these models, etc., public, or it is an IC designed by your team itself, and you want to use that in your schematic. So in all these cases, you may want to create a symbol for the IC itself, a box with n number of pins. Okay, so a new component that your team or you have got from elsewhere, for which a symbol is not there in the schematic, that you can import into the schematic. So in that case, you need to create a symbol. So the symbol editor is also there, and then the PCB layout editor. This is where you can actually place the layouts of or where the layouts are nothing but how the tracks on a final finished PCB are going to be, and where the components are going to be placed in a finished PCB. So all these informations you can specify in the PCB layout editor. Okay, and this is where a circuit or a schematic is transformed into a PCB, and the output of this will be a Gerber file which you can give to a fabricator who can actually transfer that design. So it will be something like an image itself. The output of this PCB layout editor will be something a file format similar to that of an image file format, which you can give to a third party manufacturer, PCB manufacturer, who can give it to his manufacturing tool, and the tool will take care of making a PCB in the same or that resembles the picture that you have exported out of the PCB layout editor. Okay, so the other tool that we have are a footprint editor. So similar to the symbol editor here. So in here what you need is a footprint editor. For PCB fabrication, what you need is a footprint editor. So a new IC you have designed, and it may not be a standard 8-pin or a 16-pin DIP package, and you may want to create a new package. So that you can do in this with the help of this footprint editor. And then you have a Gerber viewer. So I have told you that the output of this PCB layout editor is a Gerber format file, which is similar to which is basically an image file of how the or a mask file of how these copper traces are to be etched. So that you can view using this Gerber tool. And then there are some even less used tools in order to add graphic etc. So into the PCB itself. So your company logo or something like that, if you want to etch into the PCB, then you take the help of this tool. And then there are some calculators and page layout editor. So the layout within, so your company may want to follow a particular page layout style. So we will talk about page layout once we start looking at the schematic editor. So this is the schematic editor. Its name is eSchema. The tool's name is called as eSchema. I already told you that KiCad is a collection of tools. So many of the EDAs adopt the same philosophy, in which they have specialized tools that handle one particular job well. So eSchema does the schematic entry very well, but it doesn't know how to simulate a circuit, or it doesn't know how to create a PCB out of that. So it does one thing very well. So this same approach is used by many of the EDA tool vendors. They'll have individual tools specialized for one particular task, and then there will be file exchange format. So the schematic editor will graphically, we will be able to draw a circuit like this. Okay, and then we can export a netlist. So here we have a button to generate a netlist, and so this netlist will be input to the simulation tool. It can be the input to the PCB layout editor also. Okay, so using these kind of standard interchange file formats or file intermediates, data is exchanged between the tools within the EDA tool. Okay, and I have told you that we will discuss about the layout. So you can see that this is not just a simple sheet. It has got a certain border, and it has got a certain title information region. So all these things can be company specific. So your company may want to follow a certain format. Okay, so in that case you can edit this in that page layout editor that I was showing you. So this one, and you can add more information or remove some of the information. So among these tools, the most widely used are this one, the schematic layout editor, the PCB layout editor, and then there is one more tool which is the simulator, which can be invoked from the schematic editor itself under the tools simulator. Okay. So within this window, on the right side, you can see a lot of tools available. So first one is the arrow, which is the currently selected one. So this can be used to select particular components and like move them. Okay. So selecting components, moving them around, for all these things, you can use this cursor. Okay, and then you can right click and you will have a lot of options as to what all you can do with that tool. Okay, and then you have a highlight net entry, which can highlight one of these wires. So in a more complex circuit, it will become more useful. So the third tool is a place symbol tool, which can also be invoked with the help of this keyboard shortcut A. So you press the keyboard letter A and the same tool will get launched, and most of the time we, instead of going to the right and clicking that, we will use these shortcuts a lot in EDA tools. Okay, so there you can specify some of the components, like R will give me a resistor. Okay, so or 1N4148 will give me that particular diode. So similarly, you will specify the part number, or if it is a resistor, capacitor, or inductor, then R, C, or L, because these are generic devices. There is no part number associated with resistors. You just have a resistor which is of a certain resistance. Okay, so for those components you specify R, C, or L, and for all the other devices you specify the part number. And also generic devices are also available, like D, which is a symbol diode, which you can supply with you can enter the characteristics of this diode manually, and you can simulate any arbitrary diode that you want to. Okay, right. So that is the symbol selection tool, and then similarly a power port can also be placed, that is a ground or a V in or VCC, or so that is for that one. And then you can place all these wires. So that for that also there is a keyboard shortcut W, and then it will keep drawing the wires like that. And finally, if you enter it, then the wire will that wire tool will exit. And then there are many other tools which are even less used, like placing a bus, which is for more complex circuits, and then place wire taps. This is also useful when you are dealing with these buses. Okay, so these are all for buses. And place junctions, which are usually placed automatically, and labels, which is to name a particular node, and different other types of labels like global label, hierarchical label, etc. Okay, so so you know the tool that you can use in order to place symbols, and you know the tool that you can use to place ground, VCC, etc. And you know the symbol that can be used to draw connections between these components that you have already placed. Okay, so this is what is basically needed. You need to insert some of the components and you need to connect between them, and then you should be able to simulate it. Okay, so all the basic tools are present in these 3 buttons. All right, so I have already drawn a circuit here. So what I have done is I'll show 1 or 2 steps. So A, and first thing I'll insert is a voltage source. It is V source. So I have a V source model, which is its description says that it is a voltage source symbol for simulation purpose only. Okay, so there is no PCB footprint or PCB footprint available with this particular device. So it's a simulation only component. So all the other component that we'll be using will be non-simulation, will be available for both simulation as well as for PCB layout. Okay, this voltage source, you need to replace it with a voltage source circuit itself, because you cannot go and buy a ideal voltage source from the market. Okay, so there is no PCB layout available. It is only for simulation. So when you go to the PCB stage, either you will leave it as a, you will have to select a footprint associated with each of these components. What you can do is you can replace this with a footprint for a 2-pin connector, and later you can connect it to a proper voltage source circuit that you have designed. Okay, so if I give OK, then I have that particular symbol coming under my cursor. So I can move my cursor around and the symbol will follow me. Okay, and I can place it by clicking somewhere. Okay, and then if I press A again, then I get the same window to choose the symbol. So here I can specify the power devices also. So here I have told you that there are these 2 symbols, but these are essentially the same. So the power port elements like ground and VCC can also be selected from here. Okay, so let me choose ground. And I place it here. And in order to draw a line, so I can press W on my keyboard, and then I can click here. So that way a connection is formed between this voltage source, one of the pins of the voltage source, and the ground. Alright. So that way you can add more symbols. Let us add a resistor also, and so I type in R here, and the resistor symbol, the generic resistor symbol, comes here. And now it is coming in a vertical fashion. So I can rotate it by pressing the R key on my keyboard. So I press R and it is rotated now. I can keep pressing it. Okay, so it will, each time it will be rotated 90 degrees. So I can choose the right orientation, and then I can place it here. Okay, and then I place the cursor here and press the W key in order to draw a wire, W, and then the wire comes, and click here, mouse click here, in order to connect between those 2 points. Okay, so for each of these components, then there will be a lot of parameters that you can tune. So for resistor, you need to specify what resistance value you want to use it for. So I can give here as 1K. In the value field, I can give it as a 1K if I want to simulate a 1K resistor. Okay, similarly you can give whichever value you want the resistor to be, and that will appear here also. So here I am using a 16K resistor in the original circuit that I had. Okay. Similarly, for this capacitor also, there will be a parameter field. So there will be a value field where I can enter the value. I have given it as a 0.1 microfarad. So U stands for micro, and you don't need to give the last unit for any of the parameters. So you, for the resistor, you are not going to enter that it is its unit is in ohm. It is implied, it is assumed. The tool knows that it is the resistor value is going to be in ohms. So you just need to enter 1k or 1 meg or 1 milli or 1 ohm or 10, 1 or 10 or 100, whatever the value is. You don't need to give the unit at all. Okay, so here it is 0.1 micro, specifying that it is a 0.1 microfarad capacitor. The farad part is understood by the tool itself. Okay. And for the voltage source also, there can be a set of specification. So that is a more complex device. So for those kinds of more complex devices, so anything other than a capacitor, an inductor and a resistor, you need to do an edit spice model, and then you have to specify the parameters there. For sources, you have these many specifications. Okay, so what I want is a pulse waveform. Therefore, I have entered the period, the pulse width, etc., the pulse rise time, fall time, the pulse amplitude, the initial value, etc. So all those pulse related parameters, it's a pulse train that it is going to generate, and all the parameters related to that I have populated within this pulse entry. And if I wanted to have a sinusoidal waveform output from this particular source, then I should clear all these fields and I should enter the required parameters here, like the DC offset, the amplitude, the frequency, etc. Okay, so there are other waveform generation also, but if I want to use it just as a DC voltage source, just as a power supply, then I can just specify it here, how much voltage, like 10 volts or 12 volts DC. So then I just need to specify it here. Okay, and then there are some additional simulation techniques that are available, which can compute the frequency response, etc., of a circuit. And for that, this AC or this AC analysis window can also be used. This AC part can also be used. As we do more experiments, we will come to use all these additional features. For now, what you need to understand is, in order to configure a V source as a DC power supply, you just need to enter here the voltage that you want to supply and leave all the other fields blank. And if you want a pulse train as this output signal, that is a square wave output, then you need to specify all these parameters in the pulse and leave all the other fields empty. If you want a sine wave or a cosine wave, then you need to enter all those particulars here and leave all the other fields empty, like pulse, exponential and piecewise linear. All of those you keep empty, and the DC and AC part also you keep empty. And that is how you configure a V source simulation model to whatever signal you want it to output. Okay, all right. So I'll remove this partial circuit that I have built, and I'll just use this full circuit that I have already drawn. Okay, so you have understood how to draw a circuit and how to configure the different components within the circuit. So I'll remove all of these things. So I can select a particular region of the circuit diagram and press the delete key on the keyboard, and I can just delete that component or that part of the circuit. Okay, so now I have I just have the original circuit that I had within this file. So I have drawn it exactly the same way as I have shown you previously. Okay, and I have named these two nodes using this VD and VIN as a global label. I have placed these global labels at this node and this node so that I can easily identify the voltages in the simulation output. Okay, so once I have the circuit completely drawn and all the parameters entered correctly, then what I need to do is I have to save the sheet, and then I have to go to Tools, Simulator. There is one more step before that, which is to annotate all this schematic. So you can see that previously you might have noticed that this reference of the newly added resistor was R question mark. So if you add multiple such resistors, you will have multiple such R question mark. Okay, so in order to, so either you can click on individual resistors and assign it like R1, R2 like that, or you can use this annotate tool to automatically annotate. So many times you will use this auto annotate feature, and you select that and then you run this annotate, and it will assign numbers to, or counts or reference counts to each of these components. Okay, so here we have V in 1. So previously it used to be V in question mark before we ran the annotate step. So I have already ran a annotate step earlier before starting the video. That is why it was all annotated properly. So after annotation, we can use Tools, Simulator in order to bring in the simulation window. And there we have to go to Settings, and we have different analysis type here. Okay, and the most widely used one is the transient analysis. This is the same as your the typical breadboard experiments that you'll be doing. So there you want to feed the breadboard circuit with a particular signal from the function generator, and you want to analyze the output voltage waveform on a CRO. This particular experimentation is what is known as a transient analysis. Okay, so for transient analysis, what you need, because it is a simulator, you need to specify a time step. Okay, and this time step should be usually less than the smallest period within your circuit. So if your circuit is dealing with a frequency of say 1 kilohertz, this time step should be less than or equal to 1 millisecond, because 1 millisecond is a period of a 1 kilohertz waveform. Okay, so now in my circuit, it all depends upon what frequency I have configured this voltage source to be, because this is the only source of frequency here. Okay, so let me go to its spice model and see how much frequency I have configured this for. So the periodicity of the pulse train is 1 millisecond. This is what I have configured here, and pulse width is for 500 microseconds. So it will be a square wave with a 50% duty cycle. For 500 microsecond it will be high, and for the remaining 500 microsecond it will be low, totaling a period of 1 millisecond. So 1 millisecond is the minimum period that I have to simulate within my tool. Okay, so in the simulation window, in the simulation settings, I give it as say 1 millisecond. Okay, so giving a smaller value will produce a much better output, which but at the expense of more time to simulate the circuit, right? So, and then for how long you want to, the second parameter is how long you want the simulation to run. You may want it to run for just 1 second. Some circuits may take a lot longer to settle to the final output, and you may want to run the simulation for say 10 seconds. So here I just keep it as 1 second for the interest of simulation time. So if you increase the final time, then that just increases your simulation time, and the initial time I just want to collect it from 0 second onwards. And if you just want to if you simulate for, if your circuit takes a lot longer time to settle, say hundreds of seconds in order to settle to the final output, then what you can do is, because your CPU or your all the simulation data, all the waveform related data that are produced needs to be kept in memory. Sometimes what will happen is that for these circuits that take hundreds of seconds to settle, if you are going to capture all the data, then you'll run into memory overflow. You'll run out of RAM in your system. Okay, so what we will do in that case is, we will say you need to simulate all the way, but you just need to store the data from say 99 seconds onwards. Okay, and simulate up to 101 seconds. So till 99 seconds it will run the simulation, the simulator will run the simulation but discard all the waveform data, and from 99 seconds till 101 second it will continue running the simulation, and also it will store the data into the RAM. Okay, so that is what the initial time is going, its usage is going to be. So here we will simulate for 1 second, and I press OK, and then I run the simulation. Now it is running the simulation. You can see the time incrementing bit by bit. Okay, and then there are total number of data points of 54,005 data points. So if I increase the either the duration or either the final time, so if I make it to 10 seconds, then I'll have 5,40,000 number of data points. Similarly, if I reduce the time step to 0.1 milliseconds, in that case also I'll have 5,40,000 simulation data points. So more number of data points means more amount the simulation needs to run for, more amount of CPU resource it is going to take in order to get the simulation output. Alright, so my simulation has completed, but I still don't have anything in the waveform window, because I need to select the signals that needs to be observed into here. So I can do it either using this add signals tool. Sorry, so I need to run it again, I guess, because I modified in order to show you how to modify it. I have modified it. So add signals, and then I have many of these available signals, current and voltage signals coming here. So voltage at node VO. So here I have marked this VD, yeah, and V in. So these two nodes are marked. So I can VD or VO. So it may be a VO itself. So different signals can be collected. Say V in can be selected, and now it comes in the screen. It gets displayed in the screen. And then I can zoom in by selecting a small area, click and drag, and that way I can zoom into the signal, and I can observe the specifics here. The x-axis is time and the y-axis is the voltage. Right, so that way I can observe the signals. The other way is to probe from the circuit itself. So I can select this particular node. I just click here, and then I go back to the signal to the signal observation, and then I can see this green signal, which is the VO. Right? So that is how we do simulation. Okay, and this is going to be the the tool that you will use to replace your all the breadboard experiments. Okay, so there are compared to doing a bare breadboard experimentation, here you need to be a little bit more careful, especially at lower frequencies. The amount of overhead to do a proper simulation is slightly higher than that of a breadboard. Okay, at lower frequencies, you don't need to worry anything about the breadboard parasitics, and your results on a breadboard will be very close to what you will get on a PCB itself, on a finished PCB also. Okay, but in case of while drawing these schematic, you need to understand that these components, these resistors are all ideal resistors, capacitors are all ideal capacitors, and the behavior can be slightly different when it comes to a real capacitor or a resistor or inductor. So it may not have a resistance that is precisely 16K. It can have a tolerance. So capacitance can have a voltage rating. This resistor can have a power rating. So there are other metrics also that you need to take into account. So all those information is not captured here. So that you need to be aware of. So those informations can be captured, if essential, by modifying these resistors with a network that is capable of modeling that all those additional information. Like that. So majority of the cases you don't need or you can understand the effect of all those say by measuring the current through this resistor and the voltage across the resistor, and by multiplying those two, you get to know what the power dissipated on this resistor is going to be. So using such simple techniques, you can understand all the effects of all these additional parameters, and by just observing the voltage across the capacitor, you can understand whether at any point in time the voltage across the capacitor is going to shoot above the voltage specified for the capacitor. Okay, so some extra techniques are needed in the simulator. So in a breadboard, you are not caring about that, because if you are subjecting a capacitor to a high enough voltage, then the capacitor will burst, and that way you can understand that you have fed it with a higher voltage. Okay, but in here you need to be a little bit more careful. You need to see the waveform, and you have to ensure that the waveform is not exceeding the capacitor rated voltage, etc. Okay, but the real advantage is when you design high frequency circuits where a simulation can be far more closer to a PCB, or an EDA tool output waveform can be far more closer to a PCB than a breadboard circuit itself. And as I said, because of this feature, majority of the industry workflow, almost all of the industry workflow is first on the simulator and then on the real PCB or on the real chip itself. And the breadboard part is completely eliminated in most of the in almost all of the modern industry workflows. And it is this EDA tools are a set of tools that are worth understanding and being proficient on from a job perspective. All right. With that, we have covered the basics of KiCad and using that as a simulator, as a circuit simulator. All right, you can practice these things on your own, and you may end up slight hiccups at the beginning, but once you solve it, then it will be a very easy to use tool. Right. So with that, we will conclude today's discussion. Thank you.